28th chapter Esters. Now we're going to first time introduce esters to you, but what you can see in front of yourselves are different fats and liquids that are usually made up of esters. Also in this diagram, you can see some oils which can be used as flavoring agents, and most of the flavoring agents are actually ester in nature. Let's first define what an ester is. Ester is an organic compound which is formed by the reaction of an alcohol and a carboxylic acid. They have this functional group, COO. This is also written as this. This is the first functional group for you, which you will find a single bond sign before the functional group and after the functional group, which means this functional group must come in the center of the substance, organic substance. Let's prove how it comes as a center, right? So moving on, making a simple ester is very simple. We take the ethanoic acid, CH3COOH. We take ethanol, C2H5OH. We combine them to form ester in water. The combination requires a catalyst as few drops of concentrated sulfuric acid, H2SO4. It produces a liquid. That liquid has a very good fruity smell, as esters are nature's flavoring agents, so they have pretty strong smell. They can be used as solvents in nail polish and nail polish removers as well, right? So as you can see, the starting materials are ethanol and ethanoic acid. The catalyst is concentrated sulfuric acid, and conditions are that it requires a little amount of heat for the reaction to proceed. Now, the concentrated sulfuric acid isn't written to the equation because it's a catalyst. It is not consumed in the reaction. This reaction is known as esterification. We may also call it a condensation reaction because water is made when two molecules are joined together. We're going to talk about in the chapter of polymers how we call it a condensation reaction. So far, we can simply call it esterification. Talking about the reaction is reversible. So to maximize the yield of ethyl ethanoate or the ester we just produced, we often use pure ethanol and ethanoic acid. Pure ethanoic acid has a different name that is known as glacial ethanoic acid because ethanoic acid has the capability to look like glaciers as soon as the temperature is lowered a little bit. For example, if the temperature is lowered to around 10 degrees centigrade, this ethanoic acid would literally look like glacial or glaciers. Have you seen glaciers? They have a certain appearance, certain icy
Yeah,
appearance actually. So the same
yeah,
appearance is given by the ethanoic acid, right? So
yeah,
let's come to the part which is common for exams, drawing and naming esters. Now, in order to work out the structure of the ester formed by alcohol and carboxylic acid, it is easy for you if you draw the alcohol first and the carboxylic acid after. All right. What you
yeah,
need to do is to write the alcohol, but invert the carboxylic acid sideways. You would notice that most of the time you draw the carboxylic acid like this. You draw the group to the right of the substance, right? But that's not what we have done over here. We inverted it sideways. This functional group comes on the left, and this methyl part comes on the right. Make sense?
yeah,
So write the alcohol first and acid after, and make sure you invert the acid sideways. Now, take H out of the alcohol and OH out of the acid group to form water. This H in OH would react to form water. Now combine the rest by combining oxygen to carbon, and there you go, you'll get this structure. Make sense? Seems easy or
yeah,
not?
yeah,
Okay. So take H and OH, whatever atoms that you are left with, you're usually left with oxygen as an ending atom and alcohol, and the doubly bonded carbon atom as the first atom in acid. Combine them by a single bond sign, and you'll get the structure. From this structure, they have drawn colored portion so that you may understand that alcohol gives the first part of the name, and ethanoic acid gives the second part of the name. Let me tell you, it's pretty easy. From alcohol, the last suffix is -anol. Convert that suffix into -ile, ethanol into ethyl. And in a similar way, the acid has the suffix -oic acid, and you need to convert it into -OAte. Ethanoic acid, ethanoate. If you understand these conversions of alcohol and ethanoic acid or alcohol and carboxylic acid, you would always know how to come up with a name as well as how to draw the structure. All right?
Yeah.
Okay. So we need to practice it. That's why you would see that the book has a lot of practice in it. But before I go with that, let's go with the extension work first. In an esterification reaction, an H from the alcohol and OH from the acid are removed and they form water. However, this distinction is not very important at IGCSE level. If you remove OH from the alcohol and H from the acid, you would still obtain the same structure by joining the rest of the structure, and you will still obtain the same water molecule. However, it's easy if you go by a proper method, taking H out every time of alcohol and OH out every time of the acid. It would give you a symmetry of the structures. Okay?
Yeah.
Now, let's try drawing different esters. This is the ester, but if it's slightly different, it would be the same one. Name is written in the same way. It's just that it has been twisted from right to left and left to right. Okay?
Yeah.
So it would be the same name. It won't even be an isomer. So moving on, let's practice because we have a huge practice page in the next page. They give you many acids like methanoic acid, ethanoic acid, propanoic acid, and then they give you many alcohols, methanol, ethanol, propanol. And they talk about every possible product of these reactions, methanoic acid with methanol, ethanoic acid with methanol. So there are 9 different products that we have. This is a systematic practice, but I also believe at the same time in some random practice. Random practice can give you more advantage towards an unseen question. Do you remember what we did back in the book?
Yeah. No. That's interesting.
Okay, if you have the book open in front of you, that's fine by me. You can open this book or any other book which explains esterification in a similar way. All right, so let's try it by going with different examples. Let's take methanol this time along with ethanoic acid so that we are still talking about smaller structures. Okay, would you like to try it on your own? Or do you want the structures for these first?
I'll try it on my own first.
Go ahead. Remember the simple rules that we need to draw the alcohol in the same way. We don't need to do anything to the alcohol. But in case of the carboxylic acid, we're supposed to invert the structure sideways. Now, in these structures, it would be better if you are drawing the whole structure. I mean the whole thing. By that, I mean showing all the atoms and all the bonds. Don't skip it. Don't draw in a condensed form. That is somewhat difficult for the student to get the structure or the name of the ester right if you still go with condensed structures. Good. So far, so good. Ayan, that's why we emphasize upon inverting the structure sideways. If you don't invert it sideways, you make a mistake. So as you wrote the structure, now let me give you a hint. If you wrote the structure in this way, H, O, C, double bond O, CH3, if you wrote the structure like this, then you might have taken all of this to form water. Then this structure would have been correctly drawn, because right after O, you would use this, and then you would use this. That's why we insist on drawing the structure of the acid inverted sideways. If you draw the functional group on the right hand side, you might end up drawing the ester incorrectly.
Yeah.
Okay. All right. Let's before we move on to the second page for a second practice of ester compounds, can you name this ester for me?
Yeah. So this part is metha.
And
ethanol.
Methylethanate. Good. Very good. Okay, let's try another. This time we're going to go with propanol, and we are going to go with methanoic acid. Go ahead.
Would it be like this for methanoic acid?
Ethanoic acid has supposed to have two oxygen atoms.
Oh. Oh yeah. So would it be OH here?
Yeah, that can be taken as correct, but again, it's not inverted sideways. So draw the OH on the other side and H on this side. This would invert the entire structure. Hydrogen cannot make two bonds. Invert everything. Okay, let's try it this way. Ayan, why don't you draw the structure correctly in this way and then invert it in the second step? Exactly invert the structure in second step. This H comes first, this O comes after, this carbon comes over here like this, and then this hydrogen comes over here. Why don't you write the structure correctly the first time and then invert it? Because you're having a slight problem inverting the structure correctly. All right, let's try what I've written. Go ahead.
Okay, so I'll just draw the correct one now because I've done this part.
Yeah, that's good. Go ahead. Good, keep going. Well done. Let's talk about its name.
Yeah, so it would be
Propyl methanoid. That's correct. Well done. Do you need more examples to do, or are you
I think it's fine. Yeah.
okay? All right. So let's get back to the book. Now, the book gives you many examples along with the names and structures to give you a very good idea how we are supposed to go with esters. Now, let's talk about a couple of things more about the esters. So, moving forward, you should always be able to reverse this out, which means we can break down the ester, ethyl ethanoid, or any other ester for that matter, and you should be able to add the atoms to it. Now, as we were removing only H from ethyl, so when you're going with the reversal, you're supposed to add H back to this. As we were taking OH from the carboxylic acid, so during the reversal time, you're supposed to add OH to this part and at the correct place. So much so that the ethyl is converted into ethanol and the ethanoid is converted into ethanoic acid, which means we can go with the reverse reaction. In the presence of water, the ester breaks down to form its original constituents, ethanoic acid and ethanol in this specific case. Key point, the colors in the table are shown to how esters are made. The parts in reds come from alcohols, the blues are carboxylic acids. It isn't actually important which CO bond you break as long as you add H to one side and OH to the other side to give two OH groups, you'll get the same answers. All right. One OH group actually is a part of carboxylic. The other OH group is the sole OH group, which is the identification of the alcohol itself. Last but not the least, there is a hint at the bottom. When working out the alcohol and the carboxylic acid, an ester comes from the aryl bit, so tells you the alcohol part, and the OH bit tells you the carboxylic acid part. I think I have explained it already, so let's move forward. Now, esters are often described having a sweet, fruity smell. So whenever they talk about the smell of ester, this is the phrase you're going to use. Which brings us to uses of esters. Small esters like ethyl ethanoid are commonly used in solvents, but esters are most commonly used in fruit flavorings. Esters are also used as perfumes. They are volatile liquids with distinctive smells. The typical smell of bananas, raspberries, pears, and other fruits is due to the part in naturally occurring esters. Now, what chemists do is that they create artificial flavorings in perfumes using different esters and other organic compounds. Now, let's go with an activity, a practical making and testing the smell of some esters in the lab. As we are going to work in the lab, so we will require to go with a certain set of steps in order to get the smell correctly. Safety note, wear goggles and dispense the acid in the fume cupboard. Avoid all skin contact with the acid. Remember, we were using concentrated sulfuric acid, which is extremely corrosive and dangerous. Wash off immediately with plenty of cold water if you get some acid on your skin. Carefully follow the instructions as to how to smell the esters produced. Now, it's literally pretty easy to produce esters in a lab. On a test tube scale, by reacting various combinations of carboxylic acids and alcohols in the presence of few drops of concentrated sulfuric acid and a little bit of heat. The mixture has to be heated, but not by a direct Bunsen flame because the contents of the tube are flammable and can easily catch fire. That's why we need to keep a good safety note while performing this experiment. Although this one's easy, but we need to be cautious. Step one, put 1 cubic centimeter of ethanoic acid and 1 cubic centimeter of ethanol into a boiling tube. We take very small amounts so we can produce esters in small amounts as well. Plus, if we're going to take bigger amounts and the liquids are both volatile and flammable, it can be a little bit dangerous. Mix well, carefully add a few drops of concentrated sulfuric acid. Careful part is the most important part in this case. Place the boiling tube in a beaker of hot water at about 80 degrees centigrade for 5 minutes. This is the little bit of heating that was required for the reaction to proceed. Allow the contents of the tube to cool. When they cool, pour the mixture into a beaker half full of 0.5 mole per decimeter sodium carbonate. There would be some effervescence as excess acid reacts with the metal carbonate. The reason for doing this is to be able to smell the ester better. Remember, if there is some acid with the ester, you won't be able to smell the ester better. That's why we use the carbonate. The carbonate reacts with the excess of acid, leaving just the ester, which can easily be smelled then. Not much ester is likely to be formed in such a short time, and the smell of ester in the tube is going to be masked by the smell of carboxylic acid. So a layer of ester will separate and float on top of water. The acid and alcohol will mostly dissolve in water, but the ester won't. The small esters that you are likely to make in the lab float on water, which makes them easy to smell. As they will have a larger surface area, then it would be very easy to detect the sweet, fruity smell coming out of the ester. Moving on, smell the product by gently wafting the odor towards your nose with your hand. Do not put your nose near to the top of the beaker. That's the best way to smell any kinds of fume in the lab. Wafting is a pretty good idea. Putting your nose right on top of the beaker or the test tube or wherever we are performing the experiment is not a good idea in lab. Repeat this procedure for other combinations of acids and alcohols. For example, you can make butyl butanoate, which would smell like pineapple, and propyl ethanoate, which would smell like pears. So different esters would be imitating the smell of different fruits. So that's how we take the mixture in the test tube and put it on the hot water in a beaker. Or in a beaker, we may also use a china dish for this purpose. We take the solution of sodium carbonate and a thin layer of ester floats on the surface. It's pretty easy to smell it like this. Some extension work. Esters are hardly soluble in water, whereas small alcohols and carboxylic acids usually easily dissolve in water. Carboxylic acids a little less because they are partially soluble. Why? Because they are weak acids. If they were strong acids, they would easily dissolve. This is because the OH and COOH functional groups in alcohols and carboxylic acids can form special type of intermolecular force called hydrogen bonding with water molecules. The attractions between water and alcohol molecules are strong enough to dissolve these molecules. The lack of these functional groups, OH and COOH in ester, means that they form very weak interactions with water molecules and therefore will not dissolve. Now, in order to make sure that last line is explained properly, take a look at this structure of ester. This functional group does not contain a single hydrogen atom. So forming specific hydrogen bonds with water won't be possible, which will hinder its solubility in water. That's why esters are hardly soluble in water. I hope now it makes sense. Does it?
Yeah.
Okay. So moving on. In fact, this finishes the chapter. Okay, why don't you go ahead and solve the C part of question number 1 for me?